Okay, in the last class we just studied about the stack ADT. Today I will talk about another kind of list ADT which is called the queue ADT. Queue is what, now queue is not, does not require too much of an introduction. Stack, for example, you already list, you already know, you always use lists all the time in your life. And stack, for example, I mean once I gave you the example of stacking plates on a cupboard or stacking books on a desk, you know that immediately that the stack ADT is to be a last in first out kind of a data structure. Now a queue is something that you all know. You start in India, we always stand in queues for almost everything, whether it's a railway station, the bus stand, or you know, getting your registration done in your college, getting your ID card, wherever you have a whole lot of queues, and grocery store for that matter. If you go to a big bazaar or something like that, you are standing in the queue for a long time, and that is what a queue ADT is all about. What is the property of the queue ADT? It's just that the person who is at the beginning of the queue is served first, and then the next person, and so on. So this data structure is somewhat different. Unlike the original list ADT where we said you can insert anywhere and delete anywhere, and the stack ADT where we said the last person gets priority, gets deleted first, this queue ADT is one which is of the type what is called first in, first out. Okay, first in, first out. This is also known as FIFO. I was first in the queue and therefore I must be served first. Okay. In India, of course, in some places when we have a lot of unruly population, it behaves like a normal list, but in a civilized society you will have that you follow the queue principles, first in, first out. So what are the various operations that we perform? We want to perform on queue, dequeue, empty, and front. You want to find out who is there in the front of the queue. Okay. These are the 4 operations that you would like to perform. Okay. Basically, why would I want to look at on queue? Of course, a particular job has to be on queued, and dequeue when you want to remove an element from the queue. Empty queue, you want to find whether the queue is empty or not. For example, if I want to close the counter, I may decide that if I have multiple counters, let's say you're waiting at the passport office or whatever, I have multiple counters, I'd like to check whether the queue has become empty so that I can close a particular counter. Okay. And front of the queue to check who is there in the front of the queue. For example, if you go to the passport office, there is a facility Tatkal versus ordinary or whatever. So I'd like to move this person to a different queue and say don't be in this queue if you are asking for some other priority based scheme, because this is for non-priority people. Everybody has the same preference, and if you come in first, you get served first. Okay. So let's see how we can operate on this. Clearly, since the queue is also a special type of a list, we can again use the list ADT to perform the operations. So what will on queue become now? If I have a list ADT, it will say L dot insert at L dot end. We are always inserting at the end of the queue. And dequeue would be L dot delete L dot front. Okay. And empty will be L dot front, just like in the stack, equal to L dot end would be an empty queue. Front would be L dot retrieve of L dot first. So what I have shown here, I have shown you that all the operations that you want on the list can be on the queue, can be implemented using the list. So what I could do is, in my ADT I can say L is of type list and define operations on list to perform these operations on the queue. Okay. So this is the first thing that I always advise any student to do. If you have one ADT which you have implemented, which is completely debugged, then my advice is you just reuse that ADT again. So that's what I am doing again here, just like we did for the stack. I define the ADT queue in terms of the list and do operations on list to mimic the operations of the queue. That's all. Then what happens? You very quickly have a queue ADT. Okay. Let us say on the other hand, I want to implement my own ADT queue. Okay, that is what I am going to talk about now. So, what is it that we have? The operations which remove elements are DQ, front and empty, which gets from the queue, and things that put elements onto the queue. First, of course, you always have to create a empty queue. This is make null operation, and then on queue which puts elements onto the queue. In my implementation, where I have used C++, what I do is to make deletion easy. I have done a linked list implementation here. We will talk about array implementation a little later. So, in a linked list implementation as shown here, you have a pointer which points to the front of the queue and another pointer which points to the end of the queue. In this example here that I have done, what I do is, in addition to that, these are things, by the way, because you are hiding the implementation from the user of your ADT, you can do some clever things in your implementation to make some of the operations easy. What I have done in this implementation over here is, if you notice here, my make null operation, create an empty queue, I create a dummy cell. I did this for the list also, if you remember. I create a dummy cell. Then my on queue becomes insertion at the end of the dummy cell. Okay. What is the advantage of this? I do not have to check whether the queue is empty and then insert. I know that as soon as I have created an empty queue, there is one dummy cell, and therefore insertion becomes simply inserting at the end of this dummy cell. Okay. And then, so then I, let us say I have on queued one more element. So, what do? I go to the end of the queue and put another element over here. That is, I have a front pointer and I have a rear pointer. Please look at this here, there are two pointers pointing to the queue. Front points to the same location and rear points to the same location when it is empty. But what is nice is, because I have created a dummy cell, what happens is, when I create a dummy cell, the advantage is that there is always one element where both the front and rear are pointing to. It is not pointing to somewhere, it is nowhere. Okay. So, then what I do is, when I am doing the on queue, I am inserting X over here. So, what is interesting is, now front is pointing to the dummy cell, rear is pointing to the element. Now, I am on queuing one more element, then what happens? Rear is updated and Y is on queued after X and rear is updated over here. So, now what am I going to do when I do DQ? When I DQ, I remove this element. So, I keep the dummy cell as it is and DQ the element next to the dummy cell. Okay. This is the fundamental advantage of using a dummy cell, okay, and rear is pointing to Y. So, this is the advantage of implementing when I am doing a linked list expression, when I do a linked list implementation of queues. This is the big advantage of using a dummy cell to implement when you create an empty queue. This is the big advantage of it. Okay. And here is a implementation over here, and I have just given you the C++ implementation over here. So, you have a recursive data structure just as before, and notice that again I have what you call type def position. So, for example, I have said type def stux cell star position. We will see how we do this in the case of the array. In the case of the array, when I do a type def, it will be integer which will be type def to this. Basically, the user is simply going to use this type def position, just like you use a type integer, char, float for that matter. We create a new type called position. Okay, and how the implementation of position is, in this case, it is a pointer to a recursive data structure. In the case of arrays, it will be an index to an index in the element in the array. And of course, you need two positions, front and rear, because we have two pointers for this, and we have a creation of the empty queue, then you have the on queue, then you have a DQ, and then you have an operation which tells you what is there in the front of the queue, another one which tells you whether the queue is empty or not. And here is a simple implementation of how the rear is done. Rear pointer next, and then basically that wherever the rear is, you create a new element at the end of create a cell type with new element and put this element over here. DQ, what are we doing? This is the fundamental advantage. If it's empty, then you say q is empty, otherwise what do? We just simply update the front to point to the next element. Okay. What is interesting, the time complexity of all these operations, notice that there is no loop in any one of them, there is no going from the beginning of the list to the end of the list. Therefore, all these operations, this is, if you let us take on q for that matter, this is order 1, this is order 1, this is order 1, this is order 1. So, this is the form of P1 plus P2 plus P3 plus whatever. If you take each one of these as sub programs over here, then what is the time complexity of the segment? It is basically the max of all of this. Therefore, the time complexity of the on q operation is order 1. Similarly, we can argue that the time complexity of the dq operation is also order 1, and creating an empty queue, every one of these is order 1. So, this particular list implementation, it is not difficult, it only takes order 1 time. Now, additionally, sometimes, for example, there is also another operation that you would like to perform, which is called the queue length, which will return a value which tells you how long the queue is. Okay. Some ADTs also of the implementation of the queue also have queue length. What is the advantage of this? For example, if I am again a grocery store like Food World or something like that, I may decide, looking at the length of the queue, whether I want to increase the number of counters. Okay. So, it is a big advantage to do something like this too. So, you can also have an extra function called length. Now, if I am looking at an extra function called length, how expensive will this operation be? If you keep, so basically you will need another variable called length, which maintains the length of the queue, and then what will happen is you just keep on incrementing it when it is on queues and decrementing it when it dequeues. So, again that operation is not going to cost you more than order 1 in terms of time complexity. So, we talked about a linked list implementation of the queue. I would like to talk about an array implementation. So, what would you do with an array implementation of queues? So, let us say this is my front, this is the rear. Let us say I have an array of some particular size, let me call it some max size. Okay. I am going to leave you with this, I am not going to give you the complete implementation of this. So, this is my front, the rear. Okay. Now, I dequeue, then what happens? Front moves over here. This becomes front. Again I dequeue, this becomes front. Okay. Then let us say on queue, then maybe rear moves here. Let us say I have E, and then now I reach the end, again I rear. Okay. So, what happens is, the problem is that the queue is found somewhere between front and rear in the array. Let me say this is the, so that means if I am looking at it, if I am looking at the pink colors over here, the queue is found between front and rear. If I am looking at blue, the queue is found between front and rear, and similarly the whites give me the queue between front and rear. Alright. But the basic problem with this is, this kind of an implementation, array implementation of queue, what will happen? Very quickly you will exhaust the size of the array. What will happen is, suppose I keep on dequeuing elements, then the front comes over here and then I cannot add any more elements. Okay, this is not a good idea. So, what we normally do is that we convert this array implementation to a circular queue. This, let us say this is 1, 2, 3, 4, 5, 6 and so on, and this is the max size. Okay. This is still an array implementation, but we do what you call a logical tying of the front and the rear of the queue. So, what is the meaning now? If this is front here, this could be rear here, and it could also happen that this is front and this is rear. How do you perform this kind of arithmetic now? That means I have a circular array, and somewhere going clockwise I will find the front and the rear of the queue. Okay. So, how do you perform these operations? You guessed it right, you have to do modulo operations. Modulo based on what? Max size, to find the location of the element. So, what happens if all the time we are taking, whenever we keep incrementing, right, in the array, for example, initially let us say both front and rear are pointing to the first element, or let us say front is pointing to the first element and rear is pointing to max size or whatever, to show that it is an empty queue. I will tell you this is going to become a problem, but we will talk about it a little later. Then what are we doing? When I am going to on queue, then what am I going to do now? I am going to put the rear over here, okay, and I will put the element over here. This is front, let us say I keep on queuing. This is the front, this is the rear. Then what happens? I am always doing modulo size arithmetic. So, when it exceeds it over here, then what will happen? The rear will start overflowing onto the beginning of the array. There is a problem with this implementation. I want you to think about it. I said I start with front pointing here and rear pointing here to indicate that it is a empty queue. Now, how do we distinguish between an empty and a full queue? This becomes a problem. So, we will need another variable, or alternatively you can think of something more clever, and I would like you to think about this particular problem. Okay. So, circular queue, the advantage is that the queue is found anywhere between two indices front and rear. How are these indices computed? The indices are computed using modulo arithmetic, and the modulo is based on, so for example, I will say rear is, instead of saying rear plus 1, we will do rear plus 1 mod max size. Okay. And we have to do a little more big bookkeeping, as I already said, to distinguish between a full and an empty queue. There are two ways of doing it. You can introduce an extra variable. Okay. So, the point is, if I am using an array implementation, what is happening? The linear array, the array size gets exhausted very quickly, but the circular array, whatever is allowable in this, it will the queue can be, basically the queue moves like this. Okay. That is the fundamental property of the circular queue. It is a nice data structure, and I want you to implement all of this. Interestingly, again, all the operations on the queue can be implemented in order one time. Okay. Let me leave you with this. As I already said, implementation is a circular queue in an array. There are issues, you need to find out how to fix this, definite distinction between an empty and a full queue. Then I want you to do this as an assignment. It is nice to, simulation is a very good way of learning about ADTs, and I would like you to simulate a petrol pump. That I have a petrol pump which serves petrol for various people. Let us say you have two different petrol pumps, one for the four-wheeler and one for the two-wheeler, and for each one of them you can have arrivals that happen to the particular system. To give you an example, let us say the two-wheelers arrive very frequently. Maybe I have every I almost have a two-wheeler in every minute, whereas I may have one four-wheeler every 5 minutes or something like that. Simulate this, put it in a queue, and then on queue and dequeue, and just give statistics of how long the queue is at different intervals of time. Okay. Another very interesting implementation of queues is using the circularly linked list. That is, I am having a linked list over here, and I tie the back to the front, and I am giving you only one pointer p, okay, no two pointers. We are not going to have front and rear. I want you to implement the queue. All operations on queues must be order 1. I want you to do this. I am giving you only one pointer, no front and rear, there is only one pointer p. So, now where should p point to? Should it point to the front? Should it point to the rear? I want you to think about it. It is a circularly linked list. Okay. Now, there is one more problem which is not listed there. How would you implement a queue? See, we saw in the beginning of the class how to implement a queue using a list ADT. The question that I want to ask you is, how do you implement a queue using stacks? I want to use a stack ADT. Remember, we reuse the list ADT to build a queue ADT. Can I do the same thing? After all, queue is also a list, type of list, right? Stack is also a type of list. Now, can I use the stack ADT to implement a queue ADT? What would I require? I want you to ponder about this particular problem.